Yes.
And I think a couple other people have a chem exam at 12 in the business building, so we might need to.
No worries, no worries. I understand. So. I'm trying to come up with a chemistry plan, and I'm failing badly. So.
It's okay, I am too.
My apologies about your chemistry exam, but I guess you're just going to have to suffer through it. I'm such a dork. Okay, lecture 22. All right, I'm going to prepare everybody today that the example that we're going to do today is pretty long. And it's the thing about 3D equilibrium problems, and I'll go ahead and tell you that 3D equilibrium problems are among the longest problems that we just do in statics. They're not hard, they just become a bookkeeping issue. And so I put some stuff here on the board just to make sure that we have sort of our eyes on the prize in terms of what we're doing, because I don't want us to lose sight of what we're doing and why we're doing it, because it's going to be a lot of the same stuff over and over again. And having a plan is really, really important. Okay? A little bit of housekeeping. So, bless you. A little bit of housekeeping. So, today you had homework 4.2 due, which was the fixed support homework. I hope that was pretty short. Okay. I am giving you a homework today. It is not due for a week. Okay. It is not, I'm not giving you, oh, I've got 3 days, so I'm giving you 4 problems. It's not like that. It's only one problem. Just 3D equilibrium problems just are kind of long. And what I'm doing is I'm making that homework due next Wednesday, not next Monday. So you don't have a homework due the Monday you get back. So you are welcome. Okay. I did re-record lecture 21, so I went through it. I went through it kind of fast because we had done it in class, but I wanted the playlist to be complete and whatnot. So I did re-record that and I posted that. So let's go ahead and get right into it. We're going to do reactions in 3D. Okay. Okay. So a couple things about 3D equilibrium. So we do have 6 equations to solve. We have 6 equations, 6 unknowns. I will say that big picture-wise, there is an analogy to how we're going to do a 3D equilibrium problem if you tie it to a 2D equilibrium problem. So let me just sort of make a quick point, okay? Let's say that I have a beam. And let's just put a point load here, it doesn't matter, right? Okay, how many unknown reactions do I have for this problem? 3, right? Because I have a vertical one here, a vertical one here, and I have a horizontal one here, right? Now, one of the things that we learned with this problem is that we can just start applying equations of equilibrium sort of like at will. But what we'll find, so for example, if we sum forces in the x direction, we can probably find this one pretty easily, right? If we sum forces in the y direction next, what we'll get is an equation that has 2 unknowns in it, right? So from a strategy standpoint, it was probably advantageous to sum moments first, right? Sum moments first, get one of our answers, and then substitute that expression into the remaining equation, right? There was a strategy, right? Like the order in which we did the equations made our lives easier from a computational standpoint. And the same is largely true in 3D. The problems are bigger, but the logic is the same. And in general, a piece of advice that I would give you is that when you're applying equations of equilibrium in 3D, do the moments first, okay? Because typically when we write our moment expressions, we are summing moments about a point to eliminate as many unknowns as possible, so that the ones that are left, we have less to deal with, okay? Then we can take those values and substitute them back in when we sum forces. Does that make sense? Okay. Now, one thing that is worth discussing is that in 3 dimensions, we have different boundary conditions, right? We have different support conditions to consider, okay? And if you open up your textbook, there's going to be oodles of them. And what I tend to think is that this doesn't really test your knowledge as an engineer more than it is just reading the diagrams in the book. So I tend to restrict most of my problems to one of three, I guess I would say. So I tend to use either this one, or a cable. So something like this. And don't worry, we're going to have we're going to have examples on these over the next couple of days. This ball and socket joint is sort of like a pin support in 3D. So it has unknown forces but no moments. Okay, so it freely allows rotation, but it prevents translation. So if you ever see a ball and socket joint, it's going to have an unknown reaction in the X direction, the Y direction, and the Z direction, right? A fixed support in 3D would just have reactions everywhere, right? And then a cable is only going to contain one unknown, and that's along the direction of the cable, right? You have a cable, you yank on it, what's the tension in the cable? We've already had problems like that before, so it should be pretty straightforward, okay? Does that make sense? Okay, if that makes sense, the best way of learning this stuff is to just dig in, okay? So let's digest our problem a little bit, and let's see what we got going on here. Okay, so I have a 3D reaction problem. I have a sine, it's a 5'8" sine of uniform density, so I'm also trying to pepper in these ideas of a centroid and center of gravity and all that. But I got a 5'8" sine, it weighs about 270 pounds, and it's supported by a ball and socket joint and by two cables here and here, okay? What I want to do is I want to determine the tension in each cable and the reaction at A. Now I'm technically only specifying like 5 unknowns when really if it's a 3D equilibrium problem it should have 6. But the 6th unknown is sort of going to be analogous to this. Like here's this problem and yeah there's an unknown, but what is it? 0, right? So there is an additional unknown sort of like along the z-axis this way, but because everything's sort of parallel, it'll be 0. Okay, so we're going to determine the tension in each cable and the reaction at A. Okay, everybody with me on that? So here I have on the board, I have some unknowns, and everything we have here on the board we're going to end up putting in the notebook, so it's not like you're going to miss anything if you're just watching the video. But we have here the unknowns, and then I'm going to list all the forces and all the moments. Okay, so let's talk about our unknowns. So we have the tension in each cable and the reaction at A. So I'm going to call my unknowns tension, I don't know, AC. I'm going to call it tension, I don't know, BD. And my reaction at A, okay? Now A is going to be a ball and socket joint. So A is going to have a force in the X direction, the Y direction, and the Z direction. So I'm going to say that my unknown is whatever that vector is, okay? But that's going to be my unknown, okay? Everybody with me so far? Okay. I'm going to move this up a little bit. So that's our eye on the prize. That's what we're after. Okay, let's talk about our forces, okay? And maybe what I'll do for completion is say that my forces are in pounds, okay? Yes?
So the tension, you said AC, would it be like CE? Or like...
Oh, you're right, it's CE, you're right. Sorry, you're right, it's CE. Thank you. Yeah, you're right, it's CE. Well, whoopsie. Okay, yep, it's CE. All right, yeah, CE, BD, and the vector in it. Okay, let's talk about our forces on the system. Now, this is a rigid body equilibrium problem. So the rigid body that we need to keep in equilibrium on this problem is what? What's the rigid body? It's the sine, right? This is the sine that we're trying to keep from falling down and smacking somebody on top of the head if they're walking across the street, right? So this is the rigid body. What forces are acting on this sine? How many forces are present? Well, the first is going to be whatever's going on at A, right? Okay? So there's going to be an A vector. Now, what I propose is that A is going to be AXI plus AYJ plus AZK, right? Those are unknowns, right? I don't know what this, and this is, but those are unknown forces, right? Okay. All right. Somebody, what are two other forces acting on that sign? So we have the forces here. What are two other forces? The cables, right? So in terms of like describing these vectors, how am I going to do that? So I'm going to have a vector like this, and how do we describe forces in 3D? We take the magnitude times the unit vector, right? So we're going to have to figure out what that unit vector is, right? We're also going to have figure out that unit vector too. Now I propose to you that there are 4 forces acting on this sign, and we've captured 3 of them, but we're missing one. What are we missing? The weight, right? How much does the sign weigh? 270. So how would I describe that vector in IJK format? What direction is the 270 pounds? What axis is it acting on? The y, and is it positive or negative? All right, so what I'm going to do is I'm going to say my final force is W. So these are the 4 forces on the system, right? Can somebody tell me what should happen when I sum these forces together? 0. Some of these forces should be 0. Okay. All right. Okay. All right. So let's see. Let's see what we can do here. Let's talk about moments. Okay. Now, let's go back to this problem. Why do we typically sum moments right there? Why do we sum moments here? Why? Most of the forces are going through it, and specifically most of the unknown forces are going through it. So we can isolate the other unknowns by summing moments here. So my question to you, about which point on this system should we sum moments? A. Because there's 3 unknowns, AX, AY, and AZ, all going through here, right? So if that's the case, how many cross products are we going to have to do? So we're going to have to do a cross product for this tension. We're going to have to do a cross product for this tension. And we're going to have to do a cross product for the weight. Does that make sense? So we're ultimately going to have to do 3 moments. We're going to have to do a moment for BD, a moment for CE. I did this in the wrong order. Let's do it in the order I've been doing it with everything else. So CE, BD. It doesn't really matter. I'm just trying to be consistent. And we're going to have to do a moment for this, okay? And how are we going to do that? We're going to have an R cross a force. An R cross a force. An R cross a force, okay? And what I'm going to do is I'm going to write my subscript sort of the way the textbook would do it. I'm going to say 2C from A, 2B from A, and I will say it 2W from A. So that all of the R vectors are measured from A, because that is the point about which we are summing moments, right? And when I add up these moment vectors, what should I get? 0. So everything that we see here on the board is sort of big picture. This is our goal because we're going to do a lot of calcs and a lot of computations, and I want to make sure we have our eyes on the prize. Okay. So far, so good? Okay. All right. So with that, let's go ahead and start chugging some stuff out. Okay. Doing good. All right. So I'm going to try and reduce the scrolling up and down as much as possible, but I am going to take this sign and I'm going to put some forces on it. I'm going to do some drawing. Okay? So I'm going to have this W vector. And I'm going to say it's acting right there. Why am I saying the W vector acts right here? Because that's the center of the sign, right? Okay? So we will need ultimately that vector, and that's the R W cross A, right? From the point in question to the line of action of the force, which we'll say is just the middle of the sign. Sound good? We're going to need a force like this, which we'll call that TBD. We're going to need a force like this. TCE. I'm saying CE. I think I'm going to flip that. I'm going to call that EC because it's going from E to C. So I'm going to flip that. I'm going to flip that over here too. That's
How do I know like the tension forces are like going upward instead of downward?
That's a great question. So just make sure. So why are they going upward and going downward? Because so they're a cable. Okay. So what I'm saying is, if you're holding a cable, right, you can't really push on it. You can only yank on the cable. So what I'm saying is, think about the physics of the situation. So imagine if you have a 270-pound sign that's only held up by this little hinge. It's going to fall down, right? These cables have to pick it up. That's what I'm saying. So I'm gonna change this to EC. Change these to EC. Change that to EC. Okay. All right. And oh, sorry. Then this is wrong because this needs to be to E from there. I'll get to that here in a second. Okay. All right. Last thing that I'm going to point out is there is going to be a vector at A. And so I'm going to call this right here, we'll call that AY. Call this right here AZ. And call that AX. Okay, I'll do my best to try and not keep this jumbled. Okay? Does that make sense? Okay. All right. So we will try and not do the up and down, but I'll do my best. Okay. Okay. Now the first thing I'm going to do is distance vectors. Okay. Now, why am I doing these distance vectors? I'm doing these distance vectors because what I'm trying to define are these. See, I already have this vector defined. I already have this vector defined. So if I do these, then I can define these. So what we'll do is we'll write a vector for EC and a vector for BD. We'll turn them into lambdas and then turn them into force vectors. So give me a little bit of space. Okay. So EC, okay, would you agree with me that EC, so if I'm going from E to C, let me give myself a little bit of room, from E to C. Along the x-axis, I'm going -6. Along the y-axis, +3. Then along the z, +2. Does that make sense? So would it be, I don't know, -6i plus 3j plus 2k? Is that fair? And we'll say that's feet. I'm going to put the feet right here. Okay. And for BD, from B to D, we're going -8 in the x, and then along the y, going up 4 feet, along the z, -8. So is that fair? Did I do that too fast? Everybody okay with that? So again, the x-axis is along the sine, the y-axis is up and down, and the z is sort of in the plane of the sine. So yeah, so -6, +3, +2, -8, +4, -8. Everybody good? All right, so if that's the case, what I'll do over here is I'll say, okay, the magnitude of EC is the square root of just use Pythagorean theorem. And so just so everybody's aware, some of these calcs I'm going to kind of chug for you. This is going to be 7 feet, and BD is -8 foot. (4 foot squared, all that squared. And that one is 12 feet. So in other words, that's how long each of the cables are. How are we doing? Down just a little bit. So my unit vectors I'm going to leave this actually in fractional form. So it's just going to be that over 7, that over 7, that over 7. And it's going to be -6 over 7i plus 3 over 7j plus 2 over 7k. And that is unitless. And then this is going to be and so this one I'm going to simplify a little bit, because 8 over 12 is 2/3 and 4 over 12 is 1/3. So that's going to be -2/3 plus 1/3 -2/3 unitless. Okay. So what I'm saying is now we have a description for these vectors. Okay, does that make sense? We have a description for all 4. So what I'll do is I'll basically say, okay, here are our force vectors. And so we have A we have t we'll do it like this. Three, that's three. And then don't forget we have W. Okay. So, one of the things that I had mentioned earlier is I said, make sure and sum moments first, okay? Why is that? Well, what would happen if we sum forces first? Remember how we do this? We sum all the x terms, then the y terms, then the z terms. Let's take a look at the x terms. How many unknowns do we have? 1, 2, 3. Y terms, 1, 2, 3, 1, 2, 3. We have 3 unknowns with every one of these, right? There's a lot of unknowns. The whole point of summing moments was to get rid of everything here. So let's do our moments now, okay? Now, in order to do our moments, we do need our position vectors. Okay? Now, in order to do our position vectors, so like I said, we have the following vectors that we need, a BA, an EA, and a WA. So let's see if we can do that. Let's see if we can knock these out. Fortunately, with this problem, this is going to make this really, really easy. Okay? I'm going to scroll a little bit. My apologies. So, R, B, R, E, R, W. Okay. So how would you describe the vector from A to B? What's the x term going to be? 8i. So this is 8i. What about the y term? 0. What about this one? 0. Okay, what about E? What is that going to be? 2e from A. If this is 800, what's this one going to be? 600. Okay, what about W? How far along do we go in the X? 4. What about the Y? Negative 2.5 and 0k, right? Everybody see that? So, would you agree that this is Would you agree with that? Yes.
Could you explain the weight one more time?
So, okay. So along the X, from A to here, we're going, so the whole sign is how wide? So we go halfway over, 4. Along the Y, it's 5 foot tall, so we go down 2.5. And then we don't go any this way. All right. Everybody okay with this? So here's my point with this problem, okay? And I know there's a lot here on the screen right now, but really what I'm trying to do is just make sure that we're all in line with what we need to do, right? We need to, so let's take a step back. So our strategy, what we need to find is this, and that vector, right? We're going to hold off on doing this, so we're going to sum moments. Okay, so we've described everything. So what we now need to do are 3 cross products, right? We need to cross product this, this, and this, and we need to sum them. Notice how there is no cross product related to A. Why? Like we have a cross product for this force, for this force, for this force, but not for A. Why? Because we're summing moments at A. So the so if we wanted, we could say that MA is 0 because it's force times 0, right? Does that make sense? So if you need a term there to make your notes pretty, that would be it. Okay? Make sense? All right, so let's do some cross products. Okay? Let's do them one at a time. Okay, does everybody have all this? Okay. So the nice thing about this problem is that there's lots of zeros, and zeros are very nice to multiply with because zeros make zeros. Okay, so let's do MBD. Okay, so that's going to be RBA crossed with TBD. Okay, now the way I'm going to do this is this. Okay, TBD is going to be the magnitude times the lambda. So I'm just going to stick the lambda in the cross product and stick the magnitude on the outside. So what that's going to be is it's going to be I, J, K. R is 800. And the magnitude for TBD, this was what? -2/3, 1/3, -2/3. And then stick the magnitude out here. So we'll stick the magnitude on the outside. Okay? So let's see if we can do this in our heads, right? So when we do the I, we cross out the row in the column. We're going to get 0 minus 0, right? So that's going to be 0. Okay. What about the J term? So we take that minus J. Okay. And what do we get for J? So we cross out the row and column. We get -16/3 times 0. And then for K, we get +8/3 times 0. And then don't forget, this whole thing is multiplied by TBD. So we can summarize this as -16/3 TBD times times J. Oh wait, no, that's positive. See? Plus 8/3 TBD times K. Did I do that too fast? Is everybody okay with that? I got my signs right. Okay. MEC. All right, and please, as I'm doing this, if I'm going too fast or if there's something you don't understand, you stop me and go, Dr. Mike, what are you talking about? What is this hullabaloo on the board? And please use the word hullabaloo because nobody uses that word anymore. So we're going to have REA crossed with TEC. I'm going to move that down just a tad. Got to say, you can't do that part on a whiteboard. That's kind of cool. (600), right? So 600, and then the T vector was -6/7, 3/7, and 2/7, and that's TEC equals. Okay, so we will do the same thing that we did. So for the I term, cross that out. We're going to get 0. minus J. What's going to happen with J? We're going to get what? 12/7. It's ultimately going to be negative because we got the negative on the outside. And then for the K term, we get what? 18/7. And then don't forget this is all multiplied by TEC. So we're going to get that's J. Okay. Yes, yes it is. Thank you. Bless you. And then for W, nice thing about W is there's no symbols. It's all going to be numbers when we do that. So MW okay, 4, negative 2.50, and then the vector itself was 0, minus 270. So what are we going to get for the I term? 0 and 0. The J term, we're going to get, what is that? So J, what do we get for J? We get 0, right? 0. And then K is the one that we have a value, right? And that's what? Negative 800 and 280, 1080? 1080. So watch this. All right. Would a fair way of writing this be, would that be a fair way of writing it? Now, why am I writing it with no I term? Because look at all these. Bam, bam, bam. Right? And just so we're all clear, that's in foot-pounds, right?
And we don't do A because we're summing with the moments at A, so it's like.
Because the R vector, if we wanted to write an R vector for A, it would be just nothing but zeros. Like the R vector, what we would be saying is that the R vector to A from A. So if we did that cross product, it wouldn't give us anything. Yes?
Why don't we multiply that one by, like, the W?
Like a variable?
Yeah, like, probably the TEC.
Because we know what the weight is. So the analogy to what we did up here, this would be like the symbolic analogy, is if this was -1 and W was out here. But we know what W is. It's 270. So that's a great question. And the reason why this would be -1 is what would the lambda vector be for the weight? It would just be the direction of the weight. And the direction of the weight is -y. So it would be just -j when we put the W out here. That would give you the same answer. That's a great question.
So we have the tensions on the outside because we don't know those yet?
Yes.
Okay.
Yeah, the point right now is to figure out what these are. That's what we're trying to do. We don't know what they are, okay? So the way that we're going to figure that out is recognize that the sum of these moments must be 0. So let's do that, actually. Let's do that right now, okay? Everybody ready? Can I go ahead and scroll up? Okay. Let's apply static equilibrium and see what we get. Okay, so we're going to start out with the sum of moments. Okay. Okay. So MBD was that, oh, that's wrong. Was that MEC and MW is that, right? So far so good? So what would happen if I added these vectors up? Well, why don't we do this? Why don't we look at this box and look at this box? This box is going to be the sum of y. This is going to be the sum of the moments about the z-axis, right? So I'm going to have two equations, two unknowns, right? So if I sum moments in the about the y-axis, I'm going to get that, right? And if I sum moments, so here we'll do this. Here, I'm going to get that. Or if I bring the 1080 over onto the other side, I get that. Okay. And so, what do I do with this? Plug it into the Casio FX115 ES Plus, right? 2x2 equation solver or whatever calculator that you have. And what I'll do is I'll write it as I'll write it like that, right? Okay. And what the Casio is going to do is it's going to give you an X and Y solution, right? Okay. Now what this calculator will tell you is that X is I know some of you got a chemistry class. We're going to continue on, but the calculator is going to give you this. That's what it's going to do. Y'all remember how to do that? Okay. So here, maybe what I'll do is I'll redo my little bubble because it doesn't need to be that big. So what does that tell me? TBD is 101.25 pounds. TEC is 315 pounds. So there's two of them done. There's that and that. How do we figure out the rest? What equations of equilibrium do we have left? Sum of forces, right? So what we'll do is we'll now sum forces in the x direction, or sorry, sum forces in every direction. We're going to have the A vector we're going to have the W vector and then we're going to have this. Now, how am I going to get these vectors? Remember that this is the magnitude times the lambda, right? Don't we have the lambdas? Don't we now have the magnitudes? So if I were to tell you that this is negative 67.5 I plus 33.75 J minus 67.5 K, would that really be that crazy?
So we took the answers in the green box times the lambdas, right?
Yep. And this one is minus 270 I plus 135 J plus 90 K, right? So think about it like this. Now, if I sum the columns, these are going to be pretty easy, right? I mean, take a look at the x column. AX minus 67.5 minus 270 equals 0. It's pretty easy, right? So therefore, AX is what? 337.5? If I sum forces in the y direction, I get AY minus 270 plus 33.75 plus 135 equals 0. So therefore, AY is 101.25. And then if I sum forces in the z, that is 22.5, negative 22.5. So A is 337.5 I plus 101.25 J minus 22.5 K.
In 3D, how would you show what your positive direction is for like K?
That's a good question. So for K, positive K would be along the positive z axis. So if it's negative, it's just going the other way.
Okay.
So if you want to get technical, what we could say is this, and then let me scroll up real quick. When I drew these arrows here, I was drawing AZ along the positive K. I was wrong. It's actually going that way. That's basically what that means. When I wrote that this was positive, I was assuming that it was going along the positive z-axis. And that assumption was wrong. That's what that means. So.
But in, like, in an answer, you wouldn't expect.
No, for 3D, I just want the vector.
Okay.
Yeah, for 3D, if you get that, we're good. So. Now, here's the other thing I'll say, and then I'll let you go. This was a lot, wasn't it? This is a lot to process, so much so that when you come back from break, we're just going to do another one, just to get comfortable with it, because, whew, these are a lot. Okay, sound good? All right, I'm going to pull the code up one more time. I still have a few exams. If you didn't get your exam, come see me. I'll get it to you. I'll probably bring them on Monday as well. But that's all I got, everybody. I will see you all on Monday. You get 5 days without me. So, congratulations.